Hello and welcome to the Car Care Now channel, and welcome to part 2 of how electronic fuel injection systems work in modern cars. So in the previous episode, I will leave right here in case you haven't watched it, we've determined how electronic fuel injection work in the basics. How does it get the fuel there? How does it spray it? How does it know when to spray it and what cylinder to spray the fuel in? We figured out how much fuel it's going to spray, how it's going to measure the air amount, and then we figured out how is it going to see how things are going and kind of run a self-test to see are we doing our job well or not. But then we left off at a problem. That problem is, how does the computer actually determine, are things going well with the variables, with the extreme variables over a long period of time? And the biggest question with that is, how does the computer tell when things are going well, we have just variances from just wear and tear or time, or do we have a problem where a computer cannot control? And that is what we're going to start with in this video right after this. As computers get more advanced and more sophisticated and more complicated at the same time, they can handle more. So the idea here is the computers gain something very important. They not only execute a program, 1, 2, 3, 4, back to 1, 2, 3, 4, and we're done. They now have the ability of making decisions. That is very cool. The computer can decide what's going on the fly and make micro adjustments on the fly. And here is the best way to explain this. Think of the computer as a group of kind of a board of directors meeting at a table. Things are red hot and they are making decisions on the fly. Here's one of the most important decisions. Are things normal or do we have a problem? Because the computer can only do so much when there is a problem. And this is where fuel trims are essential to the operation of the electronic fuel injection system. The fuel trim is the measure of the adjustments that the computer is making to maintain that 14.7 to 1. So here is the problem without fuel trims. The oxygen, remember we talked about how the oxygen sensor will kind of give a test result. Well, the computer is going to basically do this. It's going to do what I call the oxygen sensor dance. The oxygen sensor says we're running too lean. Okay, we're going to correct that. Wait, we're running too rich now. Okay, we're going to correct that. It's going to keep going back, forth, back, forth, back, forth. That is actually not a random occurrence. It's just going to keep doing that into infinity. It's going to actually watch that and see overall. Now the oxygen sensor dance back, forth, that is at this level. But we're talking about the board of directors, big hot shots. They are looking at the picture from up here, looking at the whole thing. How is everything going? Not just our dance right now. That is where fuel trims come. Fuel trims are actually a number that the computer lives and dies by when it comes to electronic fuel injection. That number, if we are at perfect 0, we are making 0 adjustments at all. Everything is running naturally. We have perfect conditions for 14.7 to 1. If the fuel trim number is positive, that means the current trend of the electronic fuel injection system is we are adding more fuel than the perfect ideal condition. If the fuel trim number is in the negative, that means we are adding less fuel than the perfect ideal conditions. That is kind of the overall shot of what's going on. So of fuel trim, we have two types, two very important readings. You have the short fuel trim and you have the long fuel trim. The short fuel trim is the O2 sensor dance. O2 sensor says we're running too rich. Okay. Let's go negative and cut the fuel back. But wait, now we're too lean. Let's add some more fuel. It's going to keep going back, forth. Short is live. It is the micro adjustments that the computer is making live as we go. The long fuel trim, which is the most important, is the long average of the adjustments. What is the average? How are things trending overall on a long-term basis? That is a very important thing, because the long fuel trim is actually the final determination from above, from very high up, looking at everything, of where things are going, actually. So here's the best way to explain it. You have a dog. Your dog is on a leash. You're standing in the park. You're standing. Your dog is running back, forth, back, forth, back, forth. We're good. You're not moving. That is the long field trim. You are the long field trim. Your dog is a short field trim. All of a sudden, your dog sees another dog and it starts wanting to pull you that way. You're not going to immediately move. You're going to look at the dog. It's going this way, going this way, going this way. And eventually you're going to be like, all right, let's move a little bit and see where this dog wants to take us. You're going to move to the side, and all of a sudden your dog is happy, starts running back and forth, back and forth. That's what the long field trim is. It's trying to see what is the window of adjustability that we are doing at every given situation, not the on-the-fly adjustments. Overall, what are we trending towards? I hope that part makes sense, because it is extremely important. Because if you have a problem, the short field trim will not tell you what the problem is, because we're making adjustments, and eventually, like for example, you have a giant vacuum leak. All of a sudden, you have air coming in that we did not measure. The computer doesn't know that. So, or you have a clogged injector that is not spraying properly, even though the computer thinks it's spraying properly, but it's not. Well, let's take the fuel injector clogged example as kind of a reference of how things will go south from here. Well, we have now less fuel than air. So we are running lean. The short fuel trim will follow the oxygen sensor. The oxygen sensor will all of a sudden, whoa, whoa, whoa. We have all kinds of oxygen in the exhaust. We are running lean. The short fuel trim will go, okay, we'll go positive. Let's start adding more fuel. We add a lot more fuel. The oxygen sensor says, nope, we are still running lean. Okay, let's add even more. Still running lean. Okay, well, that's the dog at the end of the leash. It's stuck to one way. That's when the long fuel trim will be like, okay, well, let me move a little bit to the positive. It feels like you need more range. We're gonna move. Eventually, the computer will actually get to a point where the long fuel trim will be a higher number, and all of a sudden the oxygen sensor says, yeah, I'm good, we're good. We're back to jumping back and forth. But if you are only relying on the short fuel trim, you're only gonna see the dance, back, forth, back, forth, back, forth. You're not gonna see which bracket are we in. This is very difficult to explain. I hope this is making sense, because when you look at the short fuel trim on the live data, it'll be jumping back, forth. You won't understand a thing. But if you look at the long trim, you're gonna know what is the average trend over a long period of time. And when there is a problem, like a completely clogged injector or a massive vacuum leak, no matter what the long trim will move, it'll still be facing one way until there is a certain cap. If your dog keeps pulling you one way, keeps pulling you one way, keeps pulling you one way, you're gonna be like, hey buddy, what's going on? Where are you trying to go here? We're already on the next park over. Where are you trying to go? Stop, we got a problem. Computer shuts down everything. That beautiful check engine light comes on and says, we are not good. And this is out of my control, because you can't just keep dumping fuel all over the place or cut the fuel completely and you're still not happy. There is a problem. That's when a computer immediately shuts off, goes into kind of a predetermined state just to keep the engine running, and check engine light comes on. That is how it uses long-term fuel trim to figure out what's going on. Now, we have figured the entire thing out. That's it. Engineers are getting their rewards. Early retirement is in our pocket. We're done. That's it. We figured the entire thing out. And it was the case until Uncle Sam's favorite cousin came knocking on the door, the EPA. Yeah, great. Congratulations, you figured it out. But now the emission standards got even more stringent. So what are you going to do about it? Direct fuel injection, or gasoline direct fuel injection, or GDI, many names for a very fancy system. This is what happens. Remember when we talked about the carburetor in part 1 and we said that it just kind of dumps the fuel and hope for the best? Technically, multi-port fuel injection is the same thing in a controlled fashion per cylinder. We are dumping that fuel in the intake runner or port leading up to the intake valve. And when the intake valve opens, that gets pulled into the engine and gone. That, with Uncle Sam's favorite cousin pushing down on us, that's too uncontrolled, too inaccurate, too random. So they came up with a new idea. Wait, instead of firing that fuel in the intake and have it kind of dribble around and go and travel all this distance, why don't we just put the injector inside the combustion chamber where it just sprays right there, right when we need it? Because everything else, how it gets the fuel, how it knows when and how much, it all remains the same. We're just going to spray it inside the cylinder. That's very simple. That is the simplest thing to do. Just move that injector, put it inside. We're done. That's it. Case closed. That's over. Not even close. Because there is one part that we forgot. This is the biggest problem, biggest challenge with direct injection. So when we were using regular port injection, spraying the fuel in the port, you don't have resistance. You're spraying it in the port, air comes in as the engine pulls it, it pulls that atomized fuel into the cylinder, and off we go. But in the combustion chamber, where there is the piston immediately right there all the time, how are you gonna spray a perfect fine mist that is designed to atomize that fuel or turn it into a vapor? Remember, we talked about this. We're not liquid gas. We want vapor. How is it going to do that when it has to fight the combustion pressure and the pressure of the piston? And we're not talking we need to spray in a little bit. No, we need a perfect pattern for this to work. Here's the biggest problem. Port injection usually runs anywhere from 40, 60, 70 psi at max. Just to give you a reference, direct injection runs at anywhere from 2,000 to 3,000 psi. And the reason for that is the pressure on the rail for that, because the injector works exactly the same way, plunger and solenoid and everything. But the pressure needs to be so high, way higher than the pressure of the combustion chamber, so we can have that perfect mist. Otherwise, we're just dribbling liquid fuel, and that doesn't work. Or worse, we're pushing the fuel back into the injector and not letting it do a thing. So direct fuel injection is actually a lot more complicated than it seems on paper. And here's why. How exactly are you going to take that little tiny baby fuel pump in the fuel tank, and that barely gets you to 70 psi in the best world? How are you going to take that to 2,000 psi? Well, here's how it's going to do that. First, the direct fuel injector is a lot heavier duty than a regular plastic port injector, because it has to withstand an enormous amount of pressure and kind of a harsh conditions. So all the lines leading up to the direct injector rail, they're all high quality metal because they need to withstand that pressure. But how do we get that pressure though? That's the main thing. Electric fuel pump in the tank sends the fuel to the front. Then that fuel goes into a mechanical, we're back to the carburetor days because that's how they used to send fuel to the carburetor, a mechanical fuel pump that is run by the cam, or different engines will have a different, but the most common is the cam. That is a very small pump that will be able to pressurize that fuel to 2,000 to 3,000 psi. Because direct injection is very directed, we don't have any wastage, we don't have any kind of lingering around. No, it's right there. As soon as the spray is gone. We don't actually need the large amount or volume of fuel. We just need it a little bit, but we need it at super high pressure. That's exactly what direct fuel injection does. If you notice, the ports are tiny for the rails. They're not big rails. And that's how it does it. Takes that fuel, that little mechanical fuel pump, pressurizes it to super high pressure, goes into the rails, and then everything else, you already know how it works. Pretty cool, right? We have seriously come a very long way since the uncontrollable dribble, that is a carburetor, and now not even the regular port injection is enough. We have direct fuel injection, which is super high tech, and it actually works. That is pretty cool. We're happy. Uncle Sam's favorite cousin is happy. That's it. We got it. Or we thought we did, until one of the biggest discoveries in 2005 quietly was thrown into the market by the company that folks will expect them the least to innovate in something like that, Toyota. The D4S system, one of the greatest inventions that many don't even think about. Let's talk about it. Toyota is usually a very conservative company. They usually last to innovate because they want to make sure that their designs are reliable, because that's what their company image is about. They don't rush things. That's historically been the case with Toyota. But not with the D4S. See, in 2005, many actually don't notice, and according to all the research that I spent a lot of time on this, they were actually the first company to do something just beautiful. They made a system that has port and direct injection at the same time. That is pretty cool. That's what the D4S system. And in 2005, they actually did an experiment, kind of behind the scenes. So they released two engines. They are identical, almost identical in design and everything. One of those engines lives to be one of the worst Toyota engines ever. Full stop. And one of them is one of the greatest inventions ever in the fuel injection world. The engine that lives to be the worst one is the 4GR FSE. Essentially identical in construction, a little bit smaller size, but identical in construction to the 2GR FSE. The 4GR FSE, V6 2.5 liter, only has direct injection, not port or direct. Then the 2GR FSE, which is identical in construction and technology, and they came out exactly at the same time, has D4S, port and direct. But that's not all. You might be wondering, wait, didn't we go to direct injection because port injection was too random? Well, they actually discovered that two things. First, there are times when it comes to emissions where port injection is actually more efficient. Then there are times where direct injection is the most efficient. But that's not the greatest discovery. The greatest discovery is there are times where we can leverage those two systems to work together to get the maximum efficiency and maximum performance out of an engine. That is the breakthrough. The second thing is there is a byproduct of direct injection. See, when you have port injectors, the fuel will run through the back of the valve and go in. The intake manifold will have a lot of oil deposits in it. That is normal from the positive crankcase ventilation and the EGR and everything. You'll have a lot of oil and gunk going into it. But when you have fuel going over the intake valve, it'll clean it up. Fuel has a cleaning effect. But when you have direct injection only, it is spraying inside the engine. It's not spraying on back of the intake valve. So over time, you actually build up carbon at the back of the valve. No engineer will actually admit that this is one of the reasons they actually did this, although it appears to be the case, because all direct injected cars will have that glob of carbon on the intake valve. That doesn't necessarily mean it's a problem, by the way. Most folks see that and, oh my God, it's the end of the world. It's not. It becomes a problem when that builds up so much that it completely clogs or makes the intake valve not close all the way or clogs the passage completely. That's only when it becomes a problem. But you will always have that big glob. They discovered that that glob actually makes turbulence as the air goes in. It makes it turbulent and it kind of throws everything off. So that is actually a byproduct of the D4S. But the biggest thing about the two experiments that we talked about, the 4GR FSE was actually designed to run on D4S, but it didn't have it. That's why it has carbon buildup problems, it has oil consumption problems, it has all kinds of problems. And it's exactly the identical engine to the 2GR FSE, smaller size. D4S has one thing that most folks actually are not aware of it. When the engine is cold, it is best to have port injection because you want the charge that's coming in that is normally cold, you want to atomize the maximum amount of fuel to go in. Remember, we talked about direct injectors not having all the capability to spray a lot. So you're going to create some turbulence and things will not be very efficient when the car is cold. But once it warms up, things are fine. But equally, when we are at full throttle, it is best to have direct injection because direct injection in high performance settings, or if you're kind of full maximum load, direct injection, when it sprays inside the cylinder, it actually has a cooling effect. So it's going to cool the charge a little bit. And that helps things become more efficient and better. Now, here is the genius part of the D4S system. When you are fully warmed up and you are running at low or medium load, driving normally, which 99% of people every single day drive like. We don't race cars every day. We don't cold start cars the entire day. We cold start a little bit, then it warms up, and we're driving the rest of the day in a warmed up state at low or medium load. They did something that is just incredible. It is extremely difficult to explain it. I am not an engineer. I try to my best to give you the simple gist of it. They leverage both systems to achieve something just beautiful. They will spray fuel from the port injector long before the intake valve actually opens. You're going to atomize that fuel. You're going to completely mix it with the air, but we're talking about a very small amount of fuel. A small amount of fuel, so little that if you send it when we don't have direct injection, it will actually run very lean because you don't have enough fuel in there. And then when the intake valve opens, it's going to pull that lean charge into the cylinder. And right at the moment before the spark plug fires, it's going to actually send a little bit of fuel right around where the spark plug is from the direct injector, creating a ring of very rich fuel right around the spark plug. So when it fires, actually the first signs of combustion, when it mixes with the second combustion, is going to create a perfect mix, but you used so little fuel to achieve the same level of power or combustion, which is going to push the piston down. And the reason they did that is efficiency, folks. This is the biggest thing. You notice almost every single model they have in 2024 has D4S. And they're very happily comfortable with emissions because of that great discovery. Many other companies have done similar systems. You see port and direct injection, yay, great. But they actually not always will do the same thing because that is the D4S magic. Just a beautiful thing. Every other manufacturer will do things a little bit differently. We know Ford does a similar system, not exactly the same, but they use dual. Hyundai has done that and others have done that, but Toyota actually pioneered that system in a way that is just beautiful, folks. I mean, I wish there was a simpler way to explain how it actually works. It's just a marvel of engineering. And even though the engineers will never admit to it, a byproduct of the system, you won't get carbon buildup and you won't get that restriction or kind of turbulence as kind of gunk built up on the intake valve. They will never admit it, but we know that that is one of the hidden reasons behind it because D4S cars don't build carbon. If you want to see that live, I'll leave that video right here where we actually investigated it. And now we have truly completed the cycle. We figured out every single problem that was thrown at the engineers. They figured it out, and now we've talked about it. And now we arrived at 2024. Emission regulations are even going further and further and further, and electric cars are looming. Are we going to go there, or is the gasoline engine going to go into the even next leap of technology and advancements? I mean, computers today have gotten so advanced. They can do so many things. It is unbelievable and it is fascinating. And to think that it all started with the giant dribble box of a carburetor, and now we have these super high-tech computers that can just spray the exact amount of fuel at the exact millisecond, exactly at the right time, just to get that maximum performance, best fuel economy, and best emissions. It's unbelievable, folks. It's just a beautiful thing, at least to me. I hope you're sharing my passion for it here. Folks, thank you so much for watching this series. I truly hope that it was educational and helpful. And before we wrap it up, I would like to ask you one question. If you like similar series and you want to see more kind of systems in cars or components, kind of delve down into in details from the beginning to 2024 or 2025 when we get there, please leave a comment below and we will look at your comments. We'll kind of go through it and develop the series and talk about it. Folks, thank you so much for watching this video, and until the next one, may the Lord bless you and keep you, and you have yourself a wonderful day.